Hi everyone, my name is Rangeet and I am present here to work with my advisor Hridesh Rajan. Today I am going to tell you about an approach to decompose deep neural network into modules to enable the reusability and the replaceability. Before we dig into the decomposition of deep neural network or DNNs into modules, we want to discuss briefly about the decomposition in software development. First, a monolithic software is a piece of code without components or pieces, whereas a decomposed software is with components or pieces that can be utilized independently. The process that decomposes a monolithic software into components and module is called the decomposition. There are a number of benefits of decomposing software into modules. One of them is enabling reusabilities. In this example, we can use the small components to build a new software with the proper interface. Replaceability. A component of the software can be replaced by another component without changing other parts or components. Independent testing, where it should be possible to test each component separately. Independent development, where it should be possible to make drastic changes to one module without the need to change others. In this work, we will show the first two aspects of the decomposition. In the current state, a model can broadly be built in two ways. First, building from the scratch. As illustrated in this example, we take a dataset with English numeric. First, we build model structure based on the developer choice and then feed the data into the model to train it. Once trained, the values associated with the nodes and edges, and the same model would be used for the prediction. However, if we want to change something in the model, we either have to retrain from the scratch, then increases the cost and the effort significantly, as training from the scratch is always very expensive, or use transfer learning. In this concept, a model trained for a dataset, let's say X, can be applied to the model another dataset, let's say Y. Here, the most common changes involve the replacement of the last layer and train with the limited set of the new data and push it to the production. So in some sense, the reusability can be achieved in this process, but somehow in a limited manner. The process increases the complexity as the significant level of expertise is needed to do so, and decrease the scalability as only if the model structure matches, the operation can be performed. Now we'll discuss a few examples of the reusability and replaceability and compare how that can be achieved with the monolithic design and the decomposed design. First, let's assume a scenario where we have a DNN model to recognize handwritten digits 0 to 9, and can we use the same model and build a DNN model for binary digit without retraining the model with the example 0 and 1. To realize the reuse scenario, first developer will build a model structure for binary digit from the scratch. Then the developer will take the training dataset for 0 to 9 and partition is to extract label training sample for 0 and 1 for the scenario. Then with the new training dataset, model will be retrained. Whereas in our approach, we will decompose the DNN into 10 modules and reuse the module responsible for creating 0 and 1 to build a binary classifier. Now, if we have a 2 DNN model for recognize 0 to 9 A to J, can we build a DNN model for recognize 0 to 9 AB? It's really a duodecimal classifier. To realize the reuse scenario, the developer will do the same. First, extract the dataset from the existing dataset and train a new model. Whereas in our case, we'll decompose 2 DNN models into modules where each module is responsible for creating a single class of output. We'll reuse 0 to 9 modules, AB modules to build a duodecimal classifier. Now, here we will discuss a scenario that needs replacing the part of the DNN model. Let's assume we have a DNN model that is doing a satisfactory job for classifying 0 to 4 and 6 to 9. Could improve its performance for 5. Could you take the logic for classifying 5 for another DNN model and replace the faulty 5 with a new part? Realizing the replacement scenario is more complicated. The developer might need to change the model structure of the model A to the structure of the model B, which has also the potential to change the model A's effectiveness for 0 to 4 and 6 to 9. Then they can replace the training sample for 5 used to train the model A with those used to train model B. Finally, a model A would be trained with the modified training data. However, by decomposing DNN model into modules, we can simply replace the module 5 in DNN module A with the module 5 from the DNN module B. Now, we'll discuss the approach to decompose the DNN model into modules. This work takes the first step towards decomposing a monolithic deep neural network into modules so that the component of the deep neural network can be reused or create another network. The approach also takes the first step towards enabling replacement of features and constraints within the DNN. Our approach is decompose a trained DNN model into modules. In this work, we focused on DNN models for multi-level classification problems. We'll refer to the single black box DNN model for all classes as the monolithic model. Our approach decomposes such models into DNN modules, one for each level in the original monolithic model. Constant identification essentially identifies those parts of the monolithic model that contribute to a special functionality or constant. To untangle the constant of the output level, one could obtain the piece of the DNN that can perform a certain task, for example, prediction of a single class, and can hide the non-dominant constant to separate that constant. Here, the monolithic model has three tangled constants, 0, 1, and 2. The goal of the constant identification step is to identify parts of the DNN that are responsible for classifying an image into 0, 1, and 2. Once we identify the parts of the DNN related to the constant, those parts still might contribute to other constants as well. We call those constants non-dominant constants. Before we decompose the DNN into modules, we need to identify the constant in a monolithic DNN and separate them to build sub-network responsible for individual constant. In this example, for constant 0, constant 1 and 2 are non-dominant constant. We identify the part of the neural network that is responsible for the dominant constant by providing inputs related to the dominant constant. Then we identify the active and inactive edges based on the assumption of using ReLU as the activation function, and any node value less than or equal to 0 is an inactive node. Then we identify edges incident to the inactive nodes and remove them. Then identify edges coming from the inactive nodes and remove them too. Tangling identification recognizes the part responsible for other constants. While constant identification can separate the part of the network that contribute to a constant, it may not be able to make the separate part functional. Using constant identification, we identify the edges that are responsible for particular constant. However, the remaining network can only classify a single constant, as all the edges corresponding to other constants are removed or updated, and the model predicts the dominant constant irrespective of the input. Thus, the resulting network becomes a single class classifier. This is akin to removing a conditional and a branch from the program, and that results in a subprogram that performs the functionality of the remaining branch, but does so unconditionally. For example, the dominant constant from 0 cannot be used as they cannot distinguish between constant of 1 and 2. To solve the problem, our insight is to identify some edges and nodes back to the constant that help us to identify inputs that don't need classification by the dominant constant. In our approach, we do so by adding the part of the non-dominant constant. Here, an imbalance is introduced while adding the number of examples from the positive and the negative output levels. First, the edges related to the dominant constant added, and the edges related to the non-dominant constant either added or updated. Similar to the previous approach of introducing imbalance to tackle the problem, here we punish the negative output levels by letting the positive output level update the edges first. Here, the negative output levels are assigned more priority over the dominant constant by swapping the order of the edge update. For this, we update the edges correspond to a non-dominant constant first, and then update the edges responsible for the non-dominant constant. Here, the edges related to the positive levels are updated than the negative ones. Furthermore, the strong negative edges are added by introducing a validation. To do so, the value of the probability has been changed from 0 to 0.01% to the 50%, while keeping the other parts of the algorithm unchanged. Constant modularization is a process of separating the parts of the monolithic model belonging to a constant into its own DNN module. Constant modularization also involves constant channeling, where the effect of the non-dominant constant within the module are channeled appropriately. Constant modularization includes the abstraction of the non-dominant constant. In this approach, we propose a technique to abstract the non-dominant constant by combining the non-dominant nodes at the output level. First, we select the non-dominant edges and replace that with the single edge and remove the rest of the nodes. Before applying the constant channeling, we remove the irrelevant nodes at the last hidden layer that only contributes to the non-dominant constant. The edges that are connected with the negative output nodes and not connected with the positive output nodes are combined into one node. The outgoing nodes from the combined node to a particular negative output node is updated with the average of all the edges incident to that negative output nodes from nodes that are connected with the negative output levels. In summary, we have decomposed a DNN model that predicts 3 English digits into 3 modules, where each module is responsible for predicting a single digit. Here we will discuss the description of the dataset, experiment settings, and the result based on the 3 research questions: how efficient our decomposition, whether usability is possible, or whether the replaceability is possible too. We have used 4 datasets. First, MNIST. The dataset comprises of various examples of handwritten digits. Fashion MNIST. The dataset comprises of different clothes like t-shirt, top, trouser, pullover, dress, etc. The third one is KMNIST. It contains images from the Japanese digits. And the fourth dataset is extended MNIST. The dataset has 2-dimensional images from the English alphabet A to Z. As our approach is based on the dense hidden layer, training a DNN model with only the dense layer does not achieve high testing accuracy. To remedy that problem and fixing the number of output levels, all the dataset under experiment, A to G later 10 are taken from the dataset. To evaluate our approach, we built 16 different handmade models. These models are trained with corresponding dataset with 50 epochs, and they have 1, 2, 3, and 4 hidden layers, each of size 49. The name of the DNN model has been represented by dataset hyphen the number of hidden layers. For example, MNIST 4, a model created for MNIST dataset with 4 hidden layers of size 49. Modularity has traditionally associated with some loss of performance. Abstraction sometimes cost in performance. Here, by answering this research question, we want to find, does decomposed DNN model have performance cost also? If we find that the decomposed module are efficient, it tells us that decomposition is not losing any performance. To answer this research question, we evaluate the 4 different proposed techniques to identify tangling constant. We utilize the best approach based on the accuracy and the Jaccard index, and use that technique to apply the constant modularization to build modules. To do so, we decompose the DNN models into modules before channeling the non-dominant constant and run them in parallel and compute the accuracy based on the voting rule. Finally, we compare the accuracy among the different techniques and the pre-trained DNN model created from the same training examples. We found that in terms of accuracy, training only the strong negative edges performed the best over all the tangling identification approach. We measured the Jaccard index to identify tangling constants among modules. We found that utilizing the TIHP technique, where the higher priority has been given to the negative example to update the edges, the lowest Jaccard index can be achieved. However, the average accuracy is being achieved by using this particular technique is 22.93, and also the 7 out of 16 scenario, the accuracy 10%. That means that the decomposed module here is only able to identify its own classes, not able to identify the rest of the 9 output levels. Now, we apply the tangling identification approach to which is the strong negative edges to the constant modularization technique. Out of 2 constant modularization technique, the one with the removing irrelevant edges performed the best. We found that the accuracy after decomposing loses 0.01% on average. Also, in 9 out of 10 cases, we are able to increase or able to get the same accuracy as the trained model. We have found that the modularity does not lose much in performance, and surprisingly, it does or the same or the better in more than half of the cases. Now, we want to find whether these models can be reused to build new DNN models and how they can perform in comparison to the model built from the scratch. If we find that the reuse can perform well, then it saves a non-trivial amount of cost and effort to build new DNN model from the pool of available modules. In this research question, we validate whether fine-grained reuse can be achieved by utilizing the decomposed module. We have two scenarios. First, inter-dataset reuse. In this scenario, we study two modules decomposed from the same DNN model and execute them in parallel to build a smaller problem and validate against the DNN model built with the dominant examples for the peak modules. Second, inter-dataset reuse. In this scenario, study modules decomposed from two different DNN models. The inter-dataset reuse evaluation has been carried on all the dataset, and each of them has 45 scenarios where we choose two constants from 10 constants from our dataset that comprises 45 examples, 10 choose 2. And we found that the 80%, 69%, 80%, 51% cases for the MNIST, fashion MNIST, extended MNIST, and KMNIST scenario, our approach does the same or the better. In overall, inter-dataset can help to gain 0.03% accuracy on average. For inter-dataset reuse, we have evaluated two scenarios, MNIST with the extended MNIST and MNIST with KMNIST. For MNIST with extended MNIST, we have found that the 5 out of 100 cases, the decompose works the better or the same. In overall, the average loss is 5.36%, where for MNIST versus KMNIST scenario, it is 8.28%. Now, similar to reusability, we want to find how replacing a part of the DNN model works in comparison to the model built from the scratch. By enabling the replacement, we can replace the faulty part of the DNN model or even build a new model without making any changes to the rest of the section of the model. In this scenario, we replace a module from a set of modules decomposed from the DNN model with a module built from the same dataset with different configuration. We evaluate this scenario by replacing each module from the least complex model based on the number of hidden layers from each dataset and replace that with a module for same output level for more complex model. Finally, you compute the composed accuracy of the modules and compare them with the accuracy of the DNN model from which the module were decomposed and the prior accuracy of the modules. We found that there is an average 0.76% drop in the accuracy when compared to the composed accuracy of the modules before replacement. While a module can be replaced with a module with the same constant, there can be a situation that needs the module to be replaced with different constant. Here we replace one module from each dataset and replace that with a module taken from a different dataset. For example, the module responsible for classifying English 1 replaced with the module for classifying Japanese digit. We have found that on overall, inter-dataset replacement loses 5.44% accuracy on average. We have discussed three research questions. First is the how efficient the decomposed modules. We found that the decomposed modules are significantly different and they perform the same or the better. For the reusability research question, we found that reusability is possible, but inter-dataset loses 8.2% accuracy on average. Whereas for the replacement scenarios, replacement is possible, but both inter and inter-dataset scenario lose accuracy. In this talk, we have discussed about the various scenarios of reusability and replaceability and compare how developer will perform and how our approach will work. Then we talked about our decomposition approach. Finally, we discussed the three research questions and we briefly discussed about all the results at a glance. The more detailed description of the results and more experiments can be found in our paper. GitHub link is been given and where are all the codes and the details has been present.